Welcome back to the course on statistical mechanics. We shall continue with our study of computer simulations as a primary method to implement the principles of statistical mechanics. In the first part, part 1, which was in the last lecture, we discussed not just the importance of computer simulations in statistical mechanics, but the basic principles, how this allows us to discuss highly complicated systems, including biological systems like proteins and DNA and other lipids. And we mentioned there that statistical mechanics has two major techniques: molecular dynamic simulation, other is Monte Carlo. They are based on two entirely different approaches and tied to our two postulates of statistical mechanics. One invokes the time averaging, that's the molecular dynamic simulation. The other invokes the ensemble averaging, which is the Monte Carlo simulations. In this sense, they are very nicely tied together. And again, the same thing, the issue of ergodic hypothesis also comes here, because sampling of both the two will very much depend, will determine the outcome and the accuracy of the result. So in this class, today's class, we'll continue with that. I mentioned in the part 1 last lecture that is a vast course. There are many books, many books on computer simulations, and there is also large number of lectures in the YouTube. I strongly recommend students to read some of the books and the lectures. In our book, we have devoted a chapter 29 on basics of computer simulation, and chapter 30 is more advanced topics of computer simulation. And we have done it somewhat differently from other people, but it's really tied very well with the course. I'll explain to you. I already explained how we use Ising model to explain the necessity and the implementation of periodic boundary condition, and we use Ising model also the method of the method or technique of minimum image that we use to count the interactions and minimize the load on the computer. Today, we now again this same classification, molecular dynamics and Monte Carlo, but today we'll go detail now into the methods. Now, as I told you, is a time averaging. We have to generate temporal trajectory. The way we generate temporal trajectory is by solving Newton's equation in classical mechanics. And the Newton solution, equation force and mass time acceleration. So the method is just solving numerically, propagating a second order differential equation. You go to each particle, finds its position, velocities, its orientation, if it is like water, then you find the force and torque on the molecule, and then from time t to next time t plus delta t, you propagate it by integrating. This is called the method of quadrature, which is solved numerically, and there are over the hundreds of years many techniques have been developed, and all of them came handy in solving, because it's very important that we propagate the equation for a very long time. As I told you, we propagate it over maybe 100 nanoseconds, sometimes in microsecond. However, individual time steps, many of you have done a finite difference method of solving the differential equations. The difference here is that that you have a large number of degrees of freedom, like we have, even if you have 1,000 argon atoms, then we have these 3,000 position coordinates and 3,000 momentum coordinates, and these forces change very quickly. So in a liquid, so the time step that we have to use is pretty small, and time steps happen in the femtoseconds. So now you see the enormity of the problem, even less than femtosecond. Let us say that we take half a femtosecond. So now I have to propagate this equation with the 16 degrees of freedom, couple degrees of freedom, by using a time step of half a femtosecond to microsecond. So it is less than 10 to the power minus 15 to 10 to the minus 6. So I have to do something of the order of this 10 orders of magnitude. So this is huge, and that is the real difficulty. How do we integrate? Well, as I said, this is the finite difference method. There is one of the popular one is the position Farley algorithm, where you both propagate. First, you propagate the position t plus delta t, and you write the scalar expansion. Then you write t minus delta t. The whole idea is to add them and get rid of the linear term. So I get r t plus delta t, and then 2 rit minus rt minus delta t, just adding the two. So right now I do not have the this is the position algorithm. This is I don't I also get rid of, when I get rid of the first term, linear term, I get rid of also the velocity, but I do have acceleration in AIT. So this is called position Pauli algorithm. Very, very neat technique. Then in this technique, velocity is obtained after you get the trajectory. Since you know positions at t delta t and t minus delta t, you know the velocity as it's given on the right hand side of the equation, and you have to store the velocity, not only because you have to check the kinetic energy, and you have to get many properties. You need the velocity. So by this way, I get the full phase space information, the motion of the trajectory in the full space. But the advantage is that I don't have to store the velocity immediately, and so I don't need it. So that has certain simplification. Then there is the velocity algorithm. This is very clever way of doing thing, that you again now you propagate both position and the velocity, and this is again cleverly, there's a cleverness in putting the velocity term by delta t by 2 at and a delta. The whole idea is essentially to minimize the error of propagation. Then leapfrog algorithm, another interesting thing where RT is very easy. The calculation of the velocity in both these two, the calculation of the velocity is the tricky thing. So here you use Vt plus half delta t is in terms of Vt minus half delta t. So it's like you are going from t minus a, so velocity and position are staggered by half delta t, and that has the advantage that by doing that your accuracy increases, and if I remember correctly, the delta t squared term is eliminated. So everything is linear in delta t up to delta t squared, means delta t squared is eliminated, and that has numerical accuracy. At one time, when we didn't computer was not that powerful, these techniques were exceedingly important, because success of your simulation depended on what technique we use, and people used many. So then integration step size, I said the classical molecular dynamic simulation is half a femtosecond to 2 femtosecond. Ab initio molecular dynamic simulation, where you solve time dependence this time step because of the quantum degrees of freedom and because of quantum coherence, is an exceedingly small time step. So these simulations cannot be done easily more than a few, even now, a few picosecond, a few tens of picosecond. Many times when we talk of very big systems, we do a coarse grain the system. Coarse grain is essentially what you do. You kind of you have a lens and you make the lens opaque. That means you now do not want the informations which are very detailed. For example, remember we did Landau's theory of order parameter, and we wrote down the free energy in terms of order parameter expansion. That is an example of coarse grain description. That means we are not going fully to position and momentum details, but we will kind of set a grid in the system. Let us say cubic grid in a three-dimensional system, and now we average over the grid, and we averaging we find out, say for example, the order parameters. Now we derive an equation of motion for the order parameter, and then we propagate that order parameter. So that also has a great merit, and it is used in systems where we do not want the atomistic details many times. Sometimes these days coarse-grained system is also done where you eliminate say about 4 or 5 degrees of freedom, like I want to do a polymer, and in polymer I have this CH3, CH2, 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 CH2. Then I can coarse grain it by first CH2 is one carbon atom, so I eliminate hydrogen. Then I can eliminate, then take the, for example, in a protein, the amino acid, the side chains become a sphere. There are then, of course, you have to pay somewhere. So when you develop a coarse grain description, the finding the force field or intermolecular potential undergoes a lot of change, because no longer you have the interaction in terms of pair atoms. So you have to also develop the force field. So that has a lot of effort goes into that. However, coming back, so these are the kind of things that we do the different integration, different quadrature technique, different propagator technique. By this kind of short time step, we generate the trajectory. Once we generate the trajectory, statistical mechanics tells us what to do with it, because we know the time averaging. We can calculate the pressure, by calculate the specific heat, by energy fluctuation, many other radial distribution function. All these things we can calculate, and then our job is done. So there's the summary of the steps. You first create a finite box, and that's what we discussed in the last lecture. And then I remember the example of the ice. Then calculate the force on each atom and molecule, and then you go through each atom and molecule, and depending on the force, and you, according to Newton's equation, depending on the force is experiencing and the Newton's equation and the some potential like Varley algorithm, you move the position and moment of each molecule. This is called updating, update the configuration. Then you have the trajectory and calculation. This is our computer Monte Carlo, which is straightforward, and often the method of choice, and most of the packages that exist in literature, most of the packages like Gromax, Charms, and all these, they essentially are they're all molecular dynamic simulations, because molecular dynamic simulation, as I explained to you, is rather straightforward. In classical simulation, it's a solution of the Newton's equations of motion, and if Newton's equations of motion, then I can propagate it very easily. However, the next technique, and a powerful technique, and often the method of choice in complex systems, if you don't want the dynamical properties, is the Monte Carlo simulation. As I discussed last day, Monte Carlo was placed in with a Campbell and Cashin and all that. So it has to do with a lot of random number generator, and it is based on ensemble average principle. But we have to let the system go to all different microscopic states. Remember, when we did the ensemble average or time average, basic idea is that in time, trajectory has to go to all corners of the phase space. And in ensemble, I have to take sufficient number of ensembles that all the microscopic states are captured, or a fair amount of microscopic states. So both have the demand. So we now discuss the Monte Carlo simulation. Okay, in the Monte Carlo simulation, more common to calculate structural and thermodynamic properties of the system. As you can read here, he stated it is a popular area in Monaco city. I thought it was from France, but I think Monaco is mostly inhabited by France. Anyway, and it's an algorithm called Monte Carlo algorithm, which was used in Metropolis algorithm, where this name was introduced. It's a method of probability theory, and it is a probability theory that guarantees many of these things. Okay, now as before, I explain the things in terms of a Ising model, and again one-dimensional Ising model. So I wrote down the one-dimensional Ising model with this Hamiltonian that we have done. And if you have a ferromagnetic interaction, then I have the Hamiltonian. That is, two up spins when two spins are parallel, the energy is less. Now, it is a wonderful thing to do a Monte Carlo simulation on this, to explain Monte Carlo simulation on that. So, first I generate a initial configuration by go to each lattice side. I call it a random number, and that has value between 0 and 1. And if it is less than 0.5, I make it up. Is greater than 0.5, I make it down. So I can arbitrarily create a configuration. This is the beauty of Ising model. Now I want to do Monte Carlo simulation. From there, I of course sample the equilibrium configurations. And in one-dimensional Ising model, additional advantage is that we have the analytical results. So whatever I get by computer simulation, I can check it. And it's actually plays a very good starting point, and I all recommend all of you to do it. This simple calculation here that I am going to outline to you. So randomly select a spin by using a random number generator. Then you find that among its neighbors we have three possible arrangements. Both the neighboring spins point downwards. Then it is an unfavorable configuration. One spin up and among its neighbors and one spin down. Both the neighbors are in the up position. Now we consider the energy of these three cases are different. So if the select spin is up directed as it is done here, energy decreases when its spin flips. By the way, this is exactly the example which has been done in my book, and I did it by all these things in terms of Ising model so that it is easy for students to understand. Now, now there is certain things in a Monte Carlo simulation. It's very important that you do a relative, that means a relative movement. That means you favor those moves, those who lower the energy. So you can easily know now that if I ferromagnetic interaction, if I spin rates the tagged spin, if I flip down, then energy decreases, and that is accepted with unique probability. Now energy remains the same. If it happens, the energy remains the same after the flip, not in this case, but if my one spin is up and another spin is down, that configuration, this will happen. And then I take that configuration, the change configuration with half probability. However, if it increases, then there are two situations, and it's very interesting. If it increases, then you accept, but you accept with the penalty. By doing these choices, you bias the system to low energy configuration. Why? Because it's Boltzmann who told us that these properties of the system are weighted by e to the power minus beta e. This is the class of the Monte Carlo simulation. So here I have showed you that if now it have two conditions, it can flips, and if it flips, then it is accepted with unit probability. However, if it is no flip, then it is like that. But however, if it flips, this picture is not 100% correct. It would be down, and down is going up. If down going up, like actually on the upper one, then energy going up. Then we accept with the probability such that probability is conserved, but with a penalty, as I told you. So flip probability, that means from raise spin down to going up, that will be in the change of energy is delta E, then e to the power minus beta delta E 1 plus e to the power minus beta delta E. And then we consider no flip. You say no. I now open the option that I'll have no spin flip. Then that will have a probability 1 minus that. So probability must be conserved. So if there energy goes up, then I have the option that I am going to stay in my same configuration. So that is given by my bottom equation. So these two must be added to unity as I show in the left. Again, to remind you, there is a mistake in the figure here. The red tag on the extreme left should actually be down. Now, what I described right now to you is the one with the spin discrete dynamics. But many times, as you know, Lennard-Jones water, we have a potential that is continuous. In that case, the way we do is very interesting. We take one of the n particles and compute all the interaction. You can easily guess what will happen compared with the interaction to all the other particles. Then we now alter the coordinates by random variables, move the particles a little bit, and then we calculate the energy. If the energy goes down, we accept it. But energy goes up, we exactly do the same thing. Again, do the if energy goes down, then you accept the move. It goes zero. Then again we do the same thing. We accept the move. Now one more thing I am saying there. We just as a model we took no slip, no flip. In this case, no flip means that we don't make these changes of my 3n position coordinates. But here we call a random number r, and if my e to the power minus delta is greater than r, then only accept. That means when the energy increase is not very large. Why we do that? Because if we keep on neglecting all the moves, then it becomes very, very demanding and we don't get good. So many times we have to go up the hill, go up little bit, then go down. So, but if I reject all the moves where energy is going up, then that will be might sometimes trap me in a very small minima, and also my statistics become poor. So in this case, even when energy goes up, we do the Boltzmann factor, and if Boltzmann factor is e to the power minus beta e is e to the power minus delta u, if that is delta is not very large and positive. So this is the technique that I just explained to you, is essentially the Metropolis algorithm that so what essentially now we are going to do that what we do need in essentially the calculation of the partition function or calculation of average. That's what in statistical mechanics is. We calculate the averages over Boltzmann factor. So in this case can be measured as a predetermined set of points in the configuration space, and then the Metropolis method construct a random walk. That's where the value of the integrand is negligible. So what we do, that when energy goes up very high, then we neglect that and we can create one more move on the one more move, or rather create a Markov chain, and then we continue. So it is as if we're propagating a trajectory, but the propagation in the trajectory is not following Newton's laws of motion. It is following Boltzmann factor, and calling a random number again and again. So this random number again and again, as I said, it has to be a Markov chain, in the sense they have to be independent of each other, and these random numbers will allow me to move every atom in a random in its own three-dimensional space, random directions and by random amount, and then I calculate the energy. So this is the Metropolis algorithm. As I said, it's completely controlled. This is what in flowchart I described. Is a little bit small, but you will be able to read, young guys. So you generate the move, calculate the energy, accept it if energy is low. If energy goes up, then accept it with a penalty. So this goes on there a little bit more detail, because one thing that we want to implement is what is called microscopic reversibility. That means you are going to a place and you should be able to come back. And that thing, since we are in equilibrium, is extremely, this is essentially the concept that introduced by Onsager in terms of microscopic reversibility. And in chemistry, you already knew it in terms of detail balance, but detail balance is not microscopic reversibility, is more detailed and much more profound. Therefore, the microscopic reversibility means the probability of going to a place and the probability of in the initial position and probability of going to new position is equal to probability of the new position into probability back, the rate of coming back. So this thing, this microscopic reversibility, is essentially what we use in chemistry all the time. K1 to P1, K1 to is P2, K1, and that going back and forth, and that has to be maintained. So that is a very important quantity. So that has to be implemented in choosing the scheme and in doing the transition probability from one state to other state, because that guarantees, very important, my point is that guarantees that you are in equilibrium, because microscopic reversibility is the condition of equilibrium. So every move must obey microscopic reversibility. Otherwise, you can go away from equilibrium. And Monte Carlo algorithm is something we study on the equilibrium system. Yes, we can study on equilibrium system, but that is required far more demanding, that we are not going to discuss. What we are discussing here is the equilibrium systems, and where microscopic reversibility must be enforced. Many studies went wrong because microscopic reversibility, both in analytical and numerical, was not obeyed. Okay, so here is the acceptance rejection. The ratio is very similar to what I did in case of Ising model, so I am not going to go into detail. But one two random number generator, this same thing I described a couple of times, but one has to make sure that you are in equilibrium and you are also increase the rate of your exploration, rate of the exploration of the configuration space. You don't want to do it so slow that you don't go anywhere. If you do not accept moves which are going up, for example, you are just will not go anywhere much of the time. Here again, the flow chart with the Monte Carlo simulation in one-dimensional Ising model. We did that before. There is an important thing that you often use, is called importance sampling. Importance sampling is a name, is that, as I told you, that problem of Monte Carlo simulation, also in molecular dynamics simulation. The problem is that once the system goes into a trap or kind of deeper minimum, the system doesn't come out of that. This is a terrible problem in molecular dynamics simulation, and many molecular dynamics simulation were wrong because the system that was simulated was stuck in the minimum. However, the minimum might be only a small part of the that particular minimum where the system is stuck, because there are many other domains which need to be explored to get an averaging, and these the kind of things are done by importance sampling. Most important is that is also rare events like the chemical kinetics, when the product reactant and the product are separated by a large barrier, by high free energy barrier.
As we have emphasized, the Monte Carlo using Metropolis algorithm essentially ensures a Boltzmann averaging over configurations and Boltzmann sampling of the configurations. Importance sampling, on the other hand, tries to go where Boltzmann probability distribution is very small. So conventional Metropolis algorithm doesn't work. As we already said, these are the rare processes like in phase transition. So if one has to go over a large free energy barrier, even obtaining the free energy barrier is very important. The way it is done is actually quite smart. You define a new distribution, you define another and you sample from the other distribution, and then so you write like here the expectation value as an integration, and you define px by gx, and now as a result of that the gx that you have, this gives you an average over the term is fx px gx, and gx now you have the freedom to choose, and so you choose the value gx that it is not small in the region that you want to probe. So this is most important, is the rare event sampling, where you do not get to the barrier region, and it is shown on the table right side that it is if you go to a large barrier, then you can go days to years to sample them. However, you can now devise a distribution like it is defined here, the e to the power wx, and that pulls you towards the distribution, and is shown here that bias is wx is shown. So bias is a harmonic placed exactly at the maximum, so that now the minimum is placed exactly at the barrier. So coupled to this, added together, allows you sample the barrier region. And this is I'm not going to go through the mathematics, but you can easily see how a new term e to the power minus wx plus minus that has to is introduced, and then you get the sampling over the this region of importance. These are rather advanced technique, but it's good to know. So there is a drawback of the importance sampling.
Then there are some issues I must quickly go through. One is that how do you keep the temperature and pressure, because these things are completely fluctuating, and these are small systems. Temperature is easy to understand. Temperature you do by rescaling the velocity, like this described here. I know it is the equipartition theorem, and I know that velocity square, average of velocity square gives the temperature. Say the temperature goes up. When temperature goes up, we scale back the temperature. There are many ways of do that. So the rescale, lowering the temperature can be done by velocity rescaling. Similarly, if temperature falls down, I can upscale the velocity. However, it is easier said than done, because you have to do it systematically, and you have to do without perturb the trajectory. That is, all these different methods have been done. First one was done by Hans Andersen, Andersen thermostat. So he considered that there is an external bath, and each molecule is undergoing a collision. So when it is actually essentially the system, as if system, the bath pervades the system, and this heat bath collision frequency given by probability, and that maintains Maxwell velocity probability distribution of the particles. Then how do you control pressure? Pressure is a little bit more tricky and a little bit more dangerous. And here, but when you do NPT simulations, even when you do NVT simulations, like we do canonical ensemble or grand canonical ensemble simulations or microcanonical. Much of the time we do microcanonical. So, but we need to get the pressure correct. So many times what we do keep a pressure and run the trajectory, stabilize the system, and then you see what is the volume. Then we remove the pressure. But before that, we need the pressure, and pressure is fixed by using barostat. Barostat is a name, as you know from experiment. And in this case, we as I said, pressure is kept constant for NPT ensemble by rescaling the box vectors. So you just like pressure is moved by having a piston, here you are control the volume of the simulations shell, and there are many that again Benson barostat. That is again use a very similar technique that Benson used here. That you have a pressure coupling barostat, and each time state. Now, instead of atoms and molecules, you are changing the coordinate of the box. It has been by Perinel and Hohmann, where you you not only change this shape, you also change the size. Actually, these are very nice history. The first computer simulation of solid state phase transition was done by Anisur Rahman, where it changed the shape, and that was then developed much more by Perinello, who worked extensively with Anisur Rahman. So you are now changing the shape, changing the volume, changing the by but by doing that, that means your system is responsive. So but doing that, you can keep the target pressure. So there are, as I said, there are lots of packages, but most of the packages are molecular dynamics packages, like Gromax, LAMS, NAMD. Charm, as I told you that in Monte Carlo simulations, most of the time you have to write your own code. Though there are some codes that are available in in different books and in papers, but you don't have packages like in. So one usually has to be more creative in doing a Monte Carlo simulation. Basically, these are the question I've been asked often when I give talk by experimentalists. Do you imagine some stage the experiments will be simulation will replace the experiment? That probably never happened, but it does tell you one thing is that simulations are getting more and more powerful. But more importantly, simulation gives you information that many times experiments do not give. That gives you microscopic information, and it gives you how molecules are interacting. So it gives you by comparing theory and theory simulation and experiments, you know whether your force field is correct, your interaction, and that's a lot. That's a lot because once you know how molecules and atoms interact, you can change the interaction by some substitution, and you can create new materials. So you are it's a very powerful technique, and I did a small job here, but I strongly recommend that you read the books and many other books are there.